And in order to populate this table, since we have a large number of atoms, albeit much smaller than what we are normally accustomed to dealing with in our daily lives, but still large for a blackboard and large for a classroom. But with these larger number of atoms, finding out these values by hand is just a task that is beyond our finite capabilities. So we would like to use the processing power of a computer, and let me show you how to do that. And I'm going to upload this MATLAB file as well, so that you can tinker with it on your own. Alright, so I would like to use this formula over here, the one that I've written on the blackboard, to first of all compute this term here. How many microstates exist when 100 quantums of energy are distributed amongst 300 oscillators? So I use MATLAB for that. And there is a formula, n choose k in MATLAB, an inbuilt formula, n choose k, that helps me determine these combinations. In the numerator, I have n is 300, q is 100, minus 1. So this is in the superscript here, n plus q minus 1. And the subscript here is q. So I put 100. So this is the syntax of MATLAB. I put q equals 100. And I see how many microstates come out for this configuration, for this macrostate. It's a really large number. It's 1.6 into 10 to the power plus 96. Such a large number of atoms, bigger than the number of atoms in the universe. It's such a huge number. So I don't worry about this 1.6, I mean this is immaterial. So I put 10 to the power 96 here. Such a large number, it's of an order of magnitude estimate. And I don't know if my computational capabilities with the finite number of bits I have in my processor are able to compute this exactly, but this is a huge, huge number. It's 10 raised to the power 10 raised to the power n, it's of that order. Now what do I put in here? If I have 0 quantums of energy distributed inside 150 oscillators, how many possibilities exist? Just one. But when I multiply these, I get a really large number. Now let's look at the second row. Still, this is going to be a really large number here. Let's check this out. So n choose k, now my n is still 300, but I have 99 quantums of energy that are going into atom A. So my q is now 99. It's something 10 to the power 95. Still huge. And this huge is being multiplied by a small number here. What do I get over here? 3? 1 quantums of energy distributed to 150 oscillators. There's 150 microstates. Number of microstates is 150 here. So still a large number, an exorbitantly large number. So again, really large numbers. Likewise here, this is going to be 1, this is going to be 10 to the power 96, this is going to be 150, this is going to be 10 to the power 95, and so on. So at the bottom of the table and at the top of the table, I'm going to get large numbers. And if I multiply these out, I'm going to get extremely large numbers here, extremely large numbers at the top, and somewhere in the middle, I might expect to get some numbers that are modest. Some modesty will reappear in the middle of the table. Okay, so instead of populating this entire table and spending a lifetime doing that, let me write I've written a program. I'm going to compute all of these rows inside the table, and I'm going to plot. I'm going to plot omega A versus QA, omega B versus QB, omega B versus QA, and this product as well. Let's see what the answer turns out to be. For two atoms, remember, I get this probability distribution. I get a hump somewhere in the middle. Okay? Yes? Modest numbers for this product. Let's see. समझ आ रही है? Alright, so let me show you the program. I'll also upload this program. Since all of you are now versed with MATLAB through your lab and through other courses, I hope you'll be able to tinker with this program, you'll be able to play with it. So now I have, if you look at the screen over here, I have defined N1 is 300 oscillators in the first system. I have 100 atoms, so 300 oscillators. I have N2 is 150, which is 50 atoms, 150 oscillators in the second nanoparticle. And then I have 100 quantums. This is my given. I would like to have 100 units of energy distributed within these two unequally sized nanoparticles. Remember, they are unequally sized. One nanoparticle has twice the number of atoms as the other. So I'm adding, not only am I increasing the number of atoms, I'm making the problem slightly asymmetric. So I'm just choosing to turn off a warning. I don't want MATLAB to be disturbed by these large numbers. So what I'm trying to do is, for Q1, which is the number of QA, which is the number of quantums in atom A, going from 0 to 1 to Q. So I'm going from here to here. Okay? I'm making up this table from here. 0 quantums in atom 1, 1 atom in quantum 1, all the way up to the total number. So I'm making an array of the number of quantums in atom 1, and I'm finding out omega A, this column, choosing by varying my Q's. So I'm just filling up this column inside the table. Okay? Then I do the same for omega B. Here is the result for omega B. So if this is inside a loop, so it automatically calculates all the rows inside the table. You should be familiar with computation of this kind. You should be able to do this. That's why I've given such a problem in one or two homeworks as well. Now I would like to make a figure. So the first figure that I would like to plot is, I would like to plot omega A. Then I would like to plot omega B. And on the x-axis I will have the Q's. Then I will plot the product of omega A and omega B. And I'm also going to plot other things, but I'm not going to show, these will come up, but I will describe the rest of the things later. So we are interested in a plot of omega A, in a plot of omega B, and a plot of omega A, omega B. And keep these plots in your mind. So in the plot of omega A, omega B, and look at the probability distribution, I have more microstates when the energy is equally distributed. Let's see what happens in our case. And there is a large probability here as well. This probability is not minute as compared to this problem. All the probabilities are of the same order. This is about 25%, this is about 15%, 10%. So these are, all of these probabilities are having a tug of war. So this is a significant probability. The smaller probabilities are still significant. They are significant minority probabilities. Okay? So now let's plot these, let's run this program. It's going to take some time. because these are large number crunching, but not too much thanks to our modern computers. So I'm going to run this file. I've given it a nice name. Okay, I need to change the path. So I move into Modern Physics 2018. Okay, I'm going to hide the other plots for the time being. Now let's look at this plot over here. The first plot that you see, now pay attention, the number of quantums in A, it's almost zero, almost zero, almost zero. So I'm plotting the microstates in A versus the number of quantums in A. It's very small here, very small here, very small here, and goes to an astronomically large value over here. So when Q is large, omega A is large. Right? So Q is large, omega A is astronomically large. Look, this is 10 to the plus 96 here. Huge change in the number of microstates. So I have more energy in A. Most of the energy, if it goes inside A, there is a huge variety of microstates that become accessible for that energy. So the number of microstates skyrockets if the energy inside A is large. So I have energy and I'm giving nanoparticle A some energy. If there is more energy, then if there's just 1 unit of energy or 0 units of energy, there's only one possibility for that energy to go inside nanoparticle A. But if there's more energy, there is a huge, astronomically large, an exorbitantly large number of microstates that become available, and that is shown by this skyrocketing omega A for large Q's in A. If I were to plot Q in A, and with respect to that I plot the number of microstates in atom B, it shows the inverse behavior. It's exactly this column flipped to the other side, because QA is 100 minus QB. If Q in A is small, Q in B is large. If Q in B is large, then the number of microstates in B is also going to be large. And this again is an astronomically large number. Okay? So I get these curves. So these are the large scale versions of these curves that I've drawn over here. Now in this curve you have a gradual increase in the number of microstates with energy. Here you have a really small number of microstates and it skyrockets towards the end. Now if I were to plot omega A multiplied with omega B, the total multiplicity, the total number of accessible microstates in this 2 nanoparticle system, and I am distributing 100 quantums of energy within these 2 nanoparticles, then the number of microstates that become, this is the total number of microstates, omega A times omega B, for this energy to distribute itself. The total number of microstates, which is just the product of these numbers, is going to show a peak. This is just the continuous large at a macroscopic version of this diagram that I've drawn over here. Now this peak has nice features. There are hardly any microstates available compared to this large peak. So this is still not zero, by the way. This is still some finite number, but compared to this exorbitant astronomical peak, these numbers are minuscule. They hardly exist. They are close to zero. So this peak exists when there is a certain Q. That Q is not 50. that Q is around 66.6 or 67. So when there are 67 quantums, or 67% of the quantums in nanoparticle A, and the remainder 33% of the quantums in nanoparticle B, in that case the number of microstates in that macrostate is maximized. So there's a huge peak here, and look at this peak compared to these feeble numbers. This peak is the only dominant peak inside this graph. This is the second law of thermodynamics, which means that the most probable macrostate, it has such a large probability compared to the other macrostates that it effectively becomes the only possibility. Let me reiterate this. The number of microstates in the most probable macrostate is so large compared to the other macrostates that this modal probability, this macrostate, becomes the only probability. There is a finite probability for other macrostates as well, but this peak is so sharp and it's so large. It's like a drag delta function. It's so large that this macrostate, which corresponds to 67 quantums in solid A and the remainder 33 quantums in solid B, becomes the only probability, becomes the only possibility. So the most probable state effectively becomes the only possible state, because the probability corresponding to it overwhelms anything else. This is the second law of thermodynamics. I'm going to explain this in so many words over and over again just now, but let me take a question first.
It's a product of differential graphs, right? So what's the magnitude of the third graph? The peak in the third graph compared to the other? Is it the magnitude the same or is it less?
You see, when you're dealing with large numbers in MATLAB or in any other computational device, very large numbers, you can't take them literally, because this is such a large number that MATLAB has a finite precision. So just imagine that these are exorbitantly large numbers. Look at this, 10 is for 110. This is 10 per 70, 10 per 90. Okay, so these numbers are of the same order of magnitude. The maximum number of microstates is the same in all three of these cases. No, not necessarily. Yes, speak up. Exactly. So why do we have... Yes, I'm going to explain that. Yes. Why? Modest means some numbers which are not so large. Any more questions? Alright, let me reiterate this because this is such a subtle concept. And then I would invite you to come to the stage and rephrase this for me. What's happening here? There is some number of microstates associated with atom A and number of microstates associated with atom B. But since we're looking at how energy is distributed across the two atoms, we would like to find out, on this graph we have the fraction of energy in atom A. The fraction of energy in atom A is also is 1 minus the fraction of energy in atom B. So this axis is, you could do either one of them. So I'm plotting on this axis the fraction of energy that is in atom A, nanoparticle A. And on this axis I'm plotting the total number of microstates corresponding to a macrostate. So here in a sense I'm plotting the macrostates, all possible macrostates. Each row is a macrostate. Okay, and these numbers are the numbers of microstates in each macrostate. Number of possible configurations, all of the same energy inside each macro state. So here I am plotting the number of microstates in each macro state, and I see that the multiplicity, let's call this the multiplicity. I don't want to use the word number of microstates over and over again. I'm calling this the multiplicity, the diversity, the multiplicity. The multiplicity peaks off at a certain energy distribution. At a certain fraction of energy, which is 67% in A and 33% in B, I see a peak in the multiplicity. And since there is a peak, here, this peak is so large that it overwhelms all other macrostates. These macrostates have almost zero probability compared to this. So this macrostate, which has a peak, this peaked macrostate becomes the only possibility that is actually realized in the system. Now if I made this into a million atoms, there are a million atoms here, this peak is going to get sharper, narrower and taller. So when I'm dealing with real objects in my macroscopic world, I get sharp peaks. And if I get sharp peaks, it means that the macrostate, the sharpest peak is the only possibility. Right? So the maximum probability effectively becomes the only possibility. That is the second law of thermodynamics, that the system would like to exchange its energy, distribute its energy in a macro state which has a maximum multiplicity. The maximum number of degrees of freedom or the maximum accessible microstates exist in whatever macro state the energy would like to go into that macro state. And since the probabilities are so large compared to others, that becomes the only choice that is realized. This is the second law of thermodynamics. Now, let me just, if you be slightly patient, more things are going to come and I'm going to answer your question as well. Whenever you deal with large numbers, in order to make those large numbers appear within our grasp, you would like to convert them to some manageable numbers. There's a mathematical operation you would like to do. What is that? Logarithm. Okay? So on the bottom row, what I've done is I've taken the log, the natural log of this multiplicity, natural log omega A. This is the graph that I get. So this is a large number. So this actually means that this number would 10 e raised power 200. So this number is really large, but when I logarithmize this, this becomes a modest looking graph. This graph captures the same information as this graph. It's just that I'm dealing it in a more sophisticated manner. I'm dealing it in a more manageable fashion through the logarithm. Here if I take a logarithm of this graph, this is what I get. Okay? And here if I take a logarithm of this graph, this is what I get. I get a peak. Here I get a peak at a particular value of Q, which is around 67. Okay? This object that I plotted here is just the natural log of the number of microstates. And this object, which is just the natural log of the multiplicity, as I've called it, the number of microstates is also called the multiplicity. This is called the entropy. This is the entropy of A, the entropy of B versus energy. This is the entropy of the total system. Now I'm going to explain this on the blackboard. Now I can take questions. Yes? Now I don't think this could be a simpler way of describing entropy, but there's more to come. Yes? Third, top row, bottom row. Omega A multiply omega B. Any more questions? Yes. So we can expect, okay, just, I think you are hooked up to this, let's ignore this. Okay. Any more questions? Yes.
Should the maximum probability correspond to a situation where the division is 50% in each system? So we're having a 67 and 33% division.
Okay, let me repeat this calculation in the following fashion. Let me do equal size nanoparticles. Let me do equal size nanoparticles. Just remember this graph. In this graph, what you're observing is that this peak is not at 50%. It's nanoparticle A has the higher share of energy. It's about 67%. And you will observe immediately that if you look at the fraction of size, so if you divide this 100 divided by 150, 100 divided by 150 is 2 over 3, that's 67%. So there is more energy inside this nanoparticle, and the distribution of energy is such that the amount of energy, the total energy, which is called the internal energy in this nanoparticle, is reflective of the size of this nanoparticle. Okay? So in the next lecture when we talk about temperature, things get really interesting. But the distribution of energy is not equal. It's equitable. It's not equal, it's equitable. Equitable means the more the number of microstates available, higher the size of A, there is more microstates available in A. There is more room for the energy to spread out, to distribute itself. So the total entropy will be maximized in such a way that more energy actually lands in nanoparticle A. And that is reflective of the size of nanoparticle A with respect to B. If I have nanoparticle A and nanoparticle B of the same size, let's see what's going to happen. I'm going to tweak my code a little bit. That's all I need to do. Okay, so remember this graph? Now I'm going to look at my code and I'm going to make the number of oscillators the same in both. 300 oscillators, which means 100 atoms in each nanoparticle. Let's see what's going to happen. Now the peak has shifted to the exact middle. I have a peak in which 50 quantums are shared in A and 50 quantums are shared in B. Now the sizes of the two nanoparticles are the same. And now there is equal distribution of energy. So the distribution of energy is such that the entropy is maximized of the total system. This is another statement of the second law of thermodynamics. That the system would like to exchange and distribute and share energy in such a way that in a state of equilibrium, when all the sharing has ceased, equilibrium has been established, the entropy, the total entropy of the system is maximized. This is another statement of the second law of thermodynamics. So, you want to maximize the multiplicity, you want to maximize the entropy. The second law of thermodynamics states that in large systems, the most probable macro state becomes effectively the only possible macro state because all of the probabilities are so small. Another thing that I would like to do is let's make this smaller and this bigger. Let's see what's going to happen. So let's turn the tables now and let's have 150 oscillators here and 300 oscillators in B. So I save this. So I don't want you to see these graphs. I don't want to break the surprise here. Alright, so now I have fewer atoms in A. And 2/3 of the atoms are actually in B inside the system. So now A, the macro state, which is the most probable, at which the peak exists in the total multiplicity as well as in the entropy, exists when there is about 33% of the energy inside nanoparticle A. This peak has now shifted. Yes. They're not ignorable because still we don't have a large, still we are talking about nanoparticles, still it's a mesoscopic system. In order to verify what my friend has said over here, let's change the number of atoms and see how the peak changes, okay? See if it gets sharper and sharper and sharper. For that purpose, I have actually written another code, simpler code. Here it is. So I have 100 atoms in each nanoparticle, 300 oscillators in each.
ब्रैकेटिंग कम है सर.
Alright, so look at this peak. I have 100 atoms in each. Okay? And I get a peak here. Now what I'm going to do, I'm going to double the number of atoms. I'm going to see what the peak looks like. So I'm going to make another graph. I cannot draw the same peak on the same graph because the numbers will change so widely that they will be difficult to plot on this graph. Okay? So now what I would like to do is, I would like to double the number of atoms. I make these oscillators 600. Let's see what I get. Let's put the two graphs together. So, first of all, you will observe that this peak gets slightly sharper, though it's not immediately visible here. The sharpness is minute because I'm still doubling the number of atoms. From 100 atoms, I'm going to 200 atoms. It's still a mesoscopic system, small system. But look at this figure here. This is 10 raised to the power 150. This is 10 to the 121. This is skyrocketing. Let's increase it even further and until my MATLAB crashes. So 1200. So this number has gone exorbitantly high, 10 to the power 179. Now if I were to actually do, say, 10 to the power 20 atoms, 1 mole of water, 18 grams, has 10 to the power 23 atoms. Perform this calculation for 10 to the power 23 atoms. This peak is going to be extremely, extremely, extremely sharp and extremely large. Okay, I can't do that here because I don't have a supercomputer. Let me see what's the maximum I could go to. Still, the peak will actually get sharper, but the effect is not visible here. So, but this, look at this number here. It's 10 to the power 278. So these possibilities are probable, but so in this range the macrostates are probable, and if you have an atom of 1200 atoms, 1200 oscillators, which means 400 atoms each, this is what you will get. Now repeat this calculation for an extremely large number of atoms inside a macroscopic solid. You will get extremely sharp peaks. You could also repeat this calculation in the log scale. So if I were to take logs here, alright, so this is a graph, actually this is a log of omega A, omega B. This is not omega A, let me change the axis here, this is logarithm. Now what you observe is this is higher number of atoms here. This is the entropy of the total system for higher number of atoms, and it has a peak. It has a maximum at a certain value of Q, which is 67. Okay? And as I increase the number of atoms, the entropy goes up. Okay? So more atoms, higher the entropy. So I get this graph versus this graph. So as I go down, it means I'm using smaller number of atoms here. So as I increase the number of atoms, the entropy of the system goes up, and the peak will actually get sharper and sharper if you were to plot the multiplicity. For the finite ranges of atoms that we're dealing with, thousands, the effect is not pronounced. For a large number of atoms, the effect is really pronounced. So now if you go back to the blackboard now, how do we state the second law of thermodynamics? QA multiplicity omega A, omega B. If I have, say, n atoms here, n by 2 atoms here, the example that we've chosen, 67% of the energy actually lies in solid A, and this function is peaked at this particular QA. So I will get a sharp peak at a particular value of QA. And that tells us the equitable distribution of energy between A and B. It's not equal distribution of energy because this has more atoms. So the key is that the system will like to change itself so that this multiplicity is maximized. This multiplicity is just the number of microstates in a macrostate. And the macrostate with the highest probability, since it's a peak here, that becomes the only possibility. So if I were to deal with a million atoms, for example, really large, even bigger than million, 10 to the power 10 atoms, this peak will look like this. If I were to use 10 to the power 10 atoms, this peak will look like this. If I were to use 10 to the power 20 atoms, this peak will actually become more like a Dirac delta function, extremely sharp. And it will be higher. This is the second law of thermodynamics. The system would like to come in a state of equilibrium. In a state of equilibrium, what happens is that only one macro state becomes the only realization. It becomes the only state that is materialized because its probability overwhelms all other possible macro states. Why does it overwhelm? Because the number of microstates or multiplicity in this most probable macro state is huge as compared to all other macro states. This is the second law of thermodynamics. And if I were to plot the entropy on this graph, on the same scale, the total entropy of the system, this entropy is going to maximize here. So this is a graph of natural log of the multiplicity, which is this number here. Natural log of omega A, omega B. This object, the natural log of the multiplicity, when I multiply this with some arbitrary constant KB. Now this is unitless because this is just the number of microstates. If I were to multiply this with KB, and Boltzmann did it for the first time, this overall object is called the entropy of the system, the total entropy of these two nanoparticles. And I also know that I can write this as KB natural log the multiplicity of A plus KB natural log the multiplicity of B. This object is called the entropy of A, this object is called the entropy of B, and that is what the total entropy is. Now if I were to plot the entropies, let me show you the graphs that I suppressed earlier. So I have 300 oscillators here, which means 100 atoms, 150 oscillators in B. And now I'm going to plot, make all the plots, and I'm going to show all of these plots to you. I've inadvertently made some changes to the plot, so I'm going to go back to an older version. Alright. So here is my graph. Here is the graph that we're all familiar with now. I have a peak. Oh, I'm using a different number of atoms. Okay, let's use the. How many atoms am I actually using here? I'm actually using. Oh, Q is 20, so I just have 100. Let's make this bigger. So let's look at this scenario here. The scenario that we've already dealt with, the multiplicity is maximized when 67% of the energy is equitably, not equally distributed among the two nanoparticles. This is the most probable macrostate. So the most probable macrostate is the one in which the energy is spread the most. Energy spread the most, is distributed the most. It is spread out in a larger number of available microstates. In other words, the entropy of the total system is maximized. Now this is the total entropy of the system. It's maximum at the value of this peak. So the entropy is maximized when Q is 67. And this is the second law of thermodynamics. This is how energy would like to distribute itself. This configuration, this macrostate has the highest probability. And if I were to increase the number of atoms, this peak would become sharper and sharper. The entropy of A with respect to QA is given by this graph. And it's not the same as this. This does not have a peak at 67%. The entropy is constantly going up. Of course it's going up as the energy is going up, because now more the energy, there are more chances of the number of microstates that become available goes up as the energy goes up. Okay? If you have fewer quanta of energy, the number of available microstates is reduced. If you have just zero quantity of energy, there is only one microstate that is possible. And the entropy of such a system is zero. Natural log of 1 is 0. So that's a pure system, that's zero entropy system with zero energy. Likewise, SB, this is the natural log of omega B versus QA is given by this sloping, downward sloping function. If I were to plot SB versus omega B, it would be a function identical to this. Just remember that here I am plotting SB versus QA. So I am doing an asymmetric plotting. If I were to plot SB versus QB, then I would get a graph identical to this. And the entropy is maximized here. Now look at these graphs, and I will explain this in more detail. All of these graphs have a certain shape. And these graphs, the shape of these graphs is such that this is where the real beauty and aesthetics of the second law of thermodynamics comes in. If I plot, here I have QA, SA. If I take 2 points on this graph, any 2 points on this graph, and I connect these points by a straight line, which is called a chord, then this chord will lie below the graph. Okay? If I look at this other plot here, SB versus QA, if I connect 2 points with the chord, any 2 points with the chord will lie below the graph. Likewise for the total entropy. So such a graph is called a concave graph. Entropy is always concave. It shows a concave graph. Always. Unless you're talking about a star or a white dwarf. So the entropy of normal objects, of real objects that we deal with on a daily basis, they have concave entropies. And this is extremely important for the second law of thermodynamics. If I had a graph of this kind, Q, A versus S, a graph of this kind, this is a strange object. Stars have graphs of this kind. This is called a convex graph. If I were to draw a chord on this graph, the chord will lie above the graph. This is called a convex graph. So this is a concave upward, a concave downward graph, and I will tell you that the slope of these graphs are really important. Let me show you this last figure before we just dissipate. Look at this graph here. And I'm going to explain this graph in the next lecture. If I look at this graph here, this is the slope of one of the graphs, SB. Sorry, this is the slope of SA. Each graph has a slope. This is the slope of the graph SA, entropy of A. The green is the slope of the graph of B. And both of them are intersecting. The slopes are intersecting at 67. So when equilibrium is established, from your basic knowledge of thermodynamics, when equilibrium is established and energy has transferred itself according to the second law of thermodynamics, what property of the two objects should be the same? When all the energy distribution has taken place, the temperature has to be the same, because then the energy transfer between the objects ceases. It stops. So this shows us that the slope of the entropy versus energy graph has something to do with temperature, because at this point when equilibrium is established, which is the most probable macro state, the two slopes intersect, the two slopes become equal. So the slope must have something to do with the temperature, something to do with the temperature. And look at this graph. This blue graph is a graph of the slope of the total entropy of the system. And it's positive, 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 positive. And it becomes zero at this equilibrium point. The slope of the total entropy has become zero. This is equilibrium. Zero slope of the total entropy means maximum entropy. The second law of thermodynamics is that the entropy is maximized, and then it becomes negative again. So all of these slopes have extremely profound consequences of how energy is transferred. The last graph is, I just want to show this graph, is here I have, if I take the inverse of the slopes, this is what I get, and the inverse of the slope is just the temperature, as I'll explain in the next lecture. So the next lecture is going to be our last lecture. One announcement about the syllabus for the final exam. I've already told you that it's going to be predominantly after the midterm, but don't put me to task if I ask some questions from before the midterm. I hope I've clarified that. Thanks a lot.